Good morning. Welcome back to microprocessor course. So in today's class, we're going to finish up the external memory that we started the last class. Then we're going to continue with memory management techniques. We're going to talk about the paging, swapping, and virtual memory and the TLB. So that is the agenda of today's class. So if you still remember last class, we talked about the external memory. We call them external memory based on their location in the computer system. They are all located outside of the main computer system, which is the opposite meaning of the internal memory that we have learned the previous this lecture number 16. So here we have some examples of external memory. We talked about the magnetic disk, the lead memory, flash memory. Today's class we're going to have a short review of this, then we finish up with the no volatile solid state new memory technologies. So before that, I'm going to check if everybody is present in today's class. So class 5, number 1, number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 6, number 1, 6, 2, 3, 5, 6, number 6, 7, 8, 10, 11, 12, 13, 16, 14, 15, 17, 20, 21, 22, class 6, number 22, 23, 24, 26, 27, 28, 29, 30, P21, 6, 15. Okay, good. All right, so as I said, we're going to finish up with the memory, external memory. Then we continue with lecture number 18, which talks about the memory management techniques. So here we go. We talked about the external memory. We mainly talked the magnetic disk, which is a circular platter with a no magnetic substrate coated into a magnetic material. So it does include the recording medium, which is there as a magnetic disk surface where the data has to be stored. Then we have the data that is stored as a tiny magnetic regions. They are all marked by N to indicate the north and S to indicate the south. Then we have a track width, which is the width of the data on the track that needed to be stored on the disk. Then here we have a picture which depicts the data organization and the formatting of the disk. We have first a track which is a circular path, and this is the place where the data needed to be stored. Then each track is divided into what we call sections, and those sections are also called sectors. Now we have a number of sectors on this track. Then between the tracks, we have inter-track gap, which is a smaller space between adjacent tracks. And these gaps, they are there to help to prevent magnetic interferences. Then between the sectors, we have what we call inter-sector gap, and these are smaller gaps between sectors. The main purpose of this intersector gap is to separate the data blocks. Now, we have seen that the disk needs to rotate. It has to rotate until the sector be under the lead or the right head. You see here we have the rotation, which has to go into the opposite of the clockwise. Then we have the Prata, and we have here a splendor. The Prata is a hard disk that contains multiple magnetic and they are mounted on this platter. So we discussed about these two disk layouts methods. We have discussed about the constant angular velocity, in which we have a disk which has to rotate at a constant speed. Then we have the track, which is divided into a number of the sector. But the main disadvantage of this disk layout method is that the outer track is bigger than the inner track, and they are all include the same number of the tracks. So now, because of that, there is a waste of storage space on the outer tracks. To solve this issue, the multiple zone recording was introduced to allow tracks to be grouped into different zones, and the outer track contain more sectors than the inner ones. That is the opposite of the previous disk layout method that we discussed to solve the issue of wasting storage space. So this is more efficient than the constant angular velocity. Then we have this legacy and advanced sector format. For the older format, we have a 512 byte. This 512 byte is for user data. Then we have a 15 byte as an overhead for the gap, the sync, and the address marked field. So, and for each sector, we have a NICC field that is 50 byte. That means we have a 577 byte for the legacy 512 byte. We have 512 byte, and this 512 byte, they are for user data. Then we have 15 byte. These 15 byte, they are for overhead. They are for overhead. They need to contain the gap, the sync, and the address mark. We call them overhead field, overhead storage. Then we have extra 50 byte, and this extra 50 byte is for the ECC. As we have seen, they need to include the ECC for parity information or error detection and the correction codes. So in total, we have a 577 byte. Now, since we have 8 sectors, the order format include how many? Order format has to include a number of 400 ECC bytes. We have 8 sectors, and each sectors include a 50 byte for ECC code. That means we have 400 byte for ECC. So this is a wasting of space. So to solve this issue, we have a new format which is a 5K byte sector. New format is 5K byte sector, and for this 5K byte sector, we only have a 100 byte. 100 byte follow ECC code. So if you try to compare with the old format, you can easily find out that we have an advantage of storing enough space. Now, we talked about the disk performance parameters. We need first to understand that the disk needs a seek time. That is the time that the disk will move the required read or write to the desired track. That is very important. Then we have the rotational latency. That is the waiting time for the desired sector to rotate under the head. That is very important as well to understand the disk performance parameters. Then we have the next important parameters when it comes to disk performance. We have the transfer time. The transfer time, which is the time required to actually read or write the data. Then we have the total block access time. We call it TB. The total block access time is equals to the seek time. That is the time that the disk requires to move the read or the write head to the desired track, plus the rotational latency. That is the time, the waiting time for the desired sector to rotate under the head. Then the next parameter that needed to be added to found the total block access time is the transfer time, the TTT, which is the time that the disk requires to read or write the data. So this is how we can find the total block access time. Now, the transfer time to or from the disk depends also on the rotation speed. That means we have the TT, which is equals to the B divided by Rn, where B is the number of bytes that needed to be transferred. And we have N, which is the total number of bytes on the track. Then we have R, which is the rotation speed. It has to be expressed in revolution per second. Now, the total, the block access time, the total block access time, it can be also expressed by the following expression. We have the total block access time, which can be equals to the seek time plus 1 divided by 2R. R is the rotation speed, which is expressed in revolution per second. Then plus B, which is the number of bytes that need to be transferred, divided by Rn. N is the total number of bytes on track. So this way we can find easily the disk performance parameters. Especially we can find the total, the block total access time. Then here we have the LED memory. The LED memory, which is a set of physical disks that need to be treated as a single logical drive. Then we have the data which is distributed across the disk using the stripping. There is a redundancy in data to allow the disk, to allow the system to retrieve the data when there is a problem. Here we have the LED 0, which is depicted by this picture on the top. And data here is split in smaller blocks that we call strips, and they are distributed across multiple disks. We see that we have strip 0 on disk 1, strip 1 on disk 1, and so on and so forth. These allow multiple disks to work simultaneously. But as you can see, for LED 0, there is no backup. There is no redundancy. Then we move on for the LED level 1, which include a mirror. We call it mirrored LED. We see that the left groups of the disk, they contain original data. Then the right one, they contain a copy of the data. So every write operation is performed on two disks. Now, you can see that the capacity of this is equals to n times the disk size. Well, n is the total number of the disk. Then we need to divide by 2 because we have a duplication. Then for LED level 2, we have a bit level slipping, and it has to use the ECC, and in this case is the Hamming code that we have run. Then we have LED level 2. We have, this is a bit slipping. We call it bit level slipping. Here we have B0, B1, B2, and B3, which are data bit. We have data bit. Then we have F0B, F0B, F1B, F2B, and so on and so forth up to F3B. Then these are what we call error correction bit. Now, this is our error correction bit. Now, we need extra disks to store parity or error correction information as depicted by this picture on the bottom. Now, for letter number 3, it is a bit interleaved parity. We can also call a byte stripping level or a bit level stripping as depicted by this picture. We have B0, B1, B2, and the B3, which are the data parts, which are the data bits. Then we have the BP, which is the parity information stored on a separate disk. As you can see, we have data bits, which are stored on separate disk. Then we have the parity information, which is also stored on a separate disk. Then the next one is level 4, which is a block level parity. But you need to understand that from LED level 3, if the disk fails, the missing data can be reconstructed using the remaining data bit as well as the parity information. Here we have a simple example to help you understand how data can be reconstructed. We have data reconstruction which can be done in these 5 drive array. Let's imagine we have the drives X0 up to X3, and these are there to store data. Then we have the parity for the E bit that can be calculated as using the following expression. This is for red number 3. We have X4, which is the parity information for E bit, which can be calculated using the X3I plus exclusive or X2I, exclusive or X1I, exclusive or X0I. Then we can find easily the parity information. Now, if suppose that the drive or the disk X1 has failed, that means we can add X4, which is the parity information, to reconstruct the X1I. So we have X1I, which is equals to X4I plus X3I. We have exclusive all X2I, exclusive all X0I. Then we can find easily X1. So this principle is applicable from LED level 3 up to LED level 6. So make sure you do remember that this principle is applicable for level 3 up to level 6. Now here we have level 4, which is a block level parity. If you try to analyze it very well, we have level 4, which is similar to level 3, but you see that level 4 uses what we call block level slipping, and we have one of the disks which is dedicated for the parity information. Now, if one of the disks is failing, the missing block can be reconstructed using the parity information as we have seen from the lead level 3. So the next level is level 5. Level 5, as you can see, it is also a block level distributed parity. And you can see that unlike level 4, the parity is not stored on one dedicated disk. Instead, we have the parity information which is distributed among the disks. Now, if there is any missing block, the block can be reconstructed using what we call the parity information as well as the remaining blocks. This is variable from level 3 up to level 6. Then the next one is, the last one is level 6, which is a dual redundancy. You see that here it is, level 6 is a bit similar to level 5, but it uses 2 parity blocks. This is very important, and they are all distributed across the disk. And we have one parity block, which is B, and another one, which is a parity block Q. And these allow recovery on 2 simultaneous disk failures. This is very important to note. Now, here we have a table which summarizes all we have learned about the different levels of lead memory. We have the category, we have the levels, we have description, then we have the disk requirements, then we have data availability. These are the summary. This is the summary of what we just discussed about the lead. Then we talked about the flash memory, which is a type of semiconductor memory and is used for both internal and external memory. And it is like intermediate memory between the EEPROM and EEPROM in terms of both cost and functionality. Here are the flash memory operation, but before we talk about the flash memory operation, it's better we understand the transistor structure. Here, the transistors exploit the semiconductor's properties, and we have a smaller voltage which is applied to the control gate to allow the current to flow. Then this voltage has to regulate a large current between the source and the drain. So this is the structure of the transistors, which is going to help us to understand the flash memory operation. Now, here we have flash memory cell in one state. If you try to compare this picture on the screen with the previous one, you can easily see that we have only the floating gate, which has been added to the transistor structure that we have seen here. Now, this is the transistor structure. You see that it doesn't include the floating gate. And for the flash memory cell in one state, we have the floating gate because it is insulated by a thin oxide layer. So initially, the floating gate does not have to interfere with the transistor is operation, but this one is the flash memory cell in one state. Then the next is to see the flash memory in 0 state. You can see that here, instead of having the floating gate, we have applied a large cloth the oxide layer, which is going to cause the electron to turn through it, and these electrons become trapped on the floating gate even if the power is connected. So this is the flash memory cell in 0 state. Of hopefully you do understand the difference between the flash memory in 0 state and the flash memory in 1 state, and you do understand what is added or what is missing, and you are able to explain what happened for the flash memory set in 0 state and what happened for the flash memory in 1 state. Now, two types of flash memory. We have NAND flash memory and NOR flash memory. But I want to remind you that the flash memory is persistent. That means it can retain the data when the power is not supplied. So this is one of the external memory system which can help users to store the data permanently. So there are two types of the flash memory, NOR and the NAND. This is very important to know that the NOR flash memory, we have each state that can be read or written to or erased individually. Then the cells are all connected to the bit lines. Now, if a memory cell, for example, this one is turned on, that means that we have the bit line that need to go low. So it is very important to note that if a memory cell is turned on by its word line, we suppose that this is the memory cell which is turned on by its word line. This is the word line number 1. That means the bit line needs to go low. This is very important to know. So this is the NOR flash memory structure, and we have its functionality which is quite similar to the NOR logic gate that we all know. Now, the next one is the NAND flash memory. For the NAND flash memory, if you try to see, we have the memory which is organized in transistors array. We have a number of 16 or 32 transistors which are arranged in series. Here you can see that we have the transistors, a number of transistors. It has to be 16 or 32, and they need to be organized in series. So this is the NAND flash memory structure. Now, the bit line needs to go low if all transistors in the corresponding word lines are turned on. This is very important to note that we need the bit line to go low if all transistors in the corresponding word line are turned on. Now, here we have two pictures to help us to understand the main differences between these two flash memory. You can see easily that these are the quantitative values, and they need to be changed every year. Now, you can see easily that we have a high speed for the write, which is different for NAND and NOR memory, and also the cost per bit, they are different. So mainly we have the NOR flash memory, which provides a high-speed random access than the NAND flash memory, and NOR flash memory can read or write data to specific location, and it can retrieve a single byte. So traditionally, this NOR flash memory is used in internal memories in embedded systems. It can also be used in microcontrollers with small program code. So for NAND flash memory, data needed to be read or written to the memory in small blocks that we call page access. Then we have, it provides a higher bit density, and it does not provide any random access for external address bus. And the data needs to be written, to be read block-wise. So that means that the unit of reading data in NAND flash memory is a block, and each block holds a number of hundreds to thousands of bits. It is suitable for external external memory, like USB drivers or memory cards, as well as solid state drivers that we're going to discuss shortly. Now, these are the two types of flash memory. Hopefully, you do understand the NAND flash memory cell, how does it work, and the NOR flash memory cell. Now, here we have the next type of memory that we needed to discuss is solid state drivers. And there are more advancement when it comes to the hard disk, because you see there is increase of using these solid state drivers. We're going to discuss why they are trying to complement the hard disk drivers or fully replace them. Now, here we have a comparison of the solid state drivers and the disk drivers. And you see that the cost of these flash solid state drivers has been decreased, and there is a higher performance when it comes to the solid state drivers if you compare with the traditional HDDs. And when it comes to the speed, copy or write speed, you see that we have a higher speed for the NAND flash drivers than the HDDs. Now, when it comes to the power, we have also less power consumption for the solid state drivers, and we have also a typical higher storage capacity if you compare to these ones. So now, the cost of the flash drivers has also been decreased. Here we have the solid state organization. The first thing that you needed to understand, there is a host system. The host system which includes the operating system, OS, and then we have the file system management, file system. Then we have what we call the input-output drivers. Input-output drivers. These are the host system. This component form what we call a host system. Then we have the solid state, which includes the controller. The controller, which is there to provide the solid state interface to the host system. Then we have the addressing. The addressing, which is there to perform the section function across the flash. Then we have the data buffer that we call also cache. And here we have also error correction module. For the data buffer or cache, it is very important that it provides high speed for random access memory component used for the speed. And for error correction module, it is there to help to retrieve the data when some errors happened while reading from the solid state memory or when writing the data to the solid state memory. Now we have the flash component. As I said before, the flash memory is used to make the solid state drivers. That is the type of the, as we can see here, the NAND flash memory is being used in external memory, such as USB drivers, memory card, and SSDs. That's why here you see the flash memory component in the SSD organization. Here we see the flash memory components. All right, so what are some advantages of SSD over the HDDs? Now, we have high performance, especially for input-output operations per second. We have also higher durability. We have also lower power consumption, which is a very important factor, because we have seen that in a computer system, power consumption is one of the current issues. Here we have a compact disk. We discussed about this one. We have the CD-ROM. We have also discussed about how it does work. We have the master disk, which is used to create a die. Then the die has to stamp copies on what we call polycarbonate disk. Then we have the finishing layers. Here we have optical disk products that include the CD-ROM, the CDR, the CD-RW, and the DVD as well. So these are the optical disk products. They are also a type of external memories. We have the specifications, and here is a simple example of the CD operation. We have the CD which needed to store the data as a pitch or length on what we call polycarbonate plastic with a reflexive aluminum layer. So these are the pitch and the length. We have seen that this helps the data to be stored on the CD on what we call polycarbonate plastic. And we have a laser which is there to read the disk, and it has to reflect differently from the pitch and the length. So we have also a photo detector which has to convert this reflection into binary information, into binary data. So this is the CD operation. Now we have the magnetic types. We discussed about this last class. And here we have the magnetic types features. We have seen that they allow sequential access, and to read record n, it must read record 1 up to n minus 1. So if the path desired record, that means the type must be rewound before reading the forwarding ones. This is very important for sequential access drivers, sequential access disks. Now, it uses what we call a direct access devices. We have discussed about memory unit of data access method. We discussed about direct access, sequential access, random access, and associative access. So these magnetic disks, it uses what we call direct access. Now, what are the new non-volatile solid-state technologies? Now, if you still remember from the memory hierarchy that we discussed, we have the static RAM, which are very fast, and if you still remember, they are very expensive. Then we have the next level of the memory, which is the DRAM, and after the DRAM we have the external memory, which are the memory that we are discussing now. We have the static RAM, SRAM. Then after the SRAM we have the DRAM. After the DRAM, we have the external memory that we are discussing in today's class. We have hard disk. So this is a short review about the memory hierarchy. Now we have to discuss about the new non-volatile solid-state memory technology. We discussed about the flash memory. It is also a kind of new flash memory, non-volatile memory technology. We have two types of flash memory, NOR flash memory, and the NAND flash memory. The next one that we needed to discuss is the STT RAM and the PC RAM, as well as the RAM. So this picture on the screen normally depicts the place of this new non-volatile RAM memory into the memory hierarchy. You see we have the static RAM here, and we have the STT RAM, which is going to be included here to improve the performance of the static RAM. And we have the NAND flash memory, which is the new non-volatile memory system, which is there as a bridge between the DRAM and the hard disk. Then as you can see, we have the increase in performance from the bottom to the top, and we have decrease in cost per bit and increase in capacity or density from the top to the bottom. So this is the common factor for the memory hierarchy. We have the performance that needed to be increased from the hard disk to the static RAM. Then we have the decrease in cost per bit from the static RAM to the hard disk. Then the next one, we needed to talk about this new no-volatile memory technology. We have here the SST RAM. We have here the SST RAM, STT RAM, which stands for spine transfer torque RAM, and is one of the types of the non-volatile memory, and its speed is between 6 up to 10 nanoseconds. This is very important. This has up to 10 nanoseconds. And its storage is using what we call a magnetic tunning junction, MTG, with 2 ferromagnetic layers. So the right mechanism, we have this memory, which is very suitable for the cache memory and the main memory. That's why you see here, it is very suitable for the cache memory and the main memory. Then the picture here on the screen, it does depict how the STT RAM store the data. We have the bit line, and we have the base L code on the bottom of this reference layer. Then we have the free layer as well. Data need to be stored on this relative magnetization. We have parallel magnetization, which is a free layer which aligns with the reference layer as well, which is the low references row resistance, which is binary 0. Then we have the anti-parallel magnetization for the free layer opposite to the reference layer, and this is to represent the higher resistance for the binary 1. Then here we have the next new non-volatile memory system, which is the PC RAM. The PC RAM. The PC stands for phrase change RAM, and this one is using what we call channel genocide alloy, which is similar to the optic storage media that we have seen, and it has to use the difference resistances, and we have these two set and reset. So when it comes to this type of memory, PC RAM, you see here on this memory hierarchy is trying to be fitted in the main memory DRAM and the NAND flash memory, which is the bridge between the main memory and the hard disk. So this is the main place of the PC RAM in the memory hierarchy. Now, here we have the PC RAM, which is a volatile memory technology, and it has to use what we call channel JIT and material that can be switched between the two different phases, the low resistance and the higher resistance to represent the binary 1. Then we have a heater element, which is used to control the phase changes of this PC RAM, slow heating and the rapid deleting. So this we offer what we call lead and write speed, which is not being observed in no volatile storage memory with higher scalability. So this is the PC RAM that we are talking about. Now, the last memory system that we needed to talk about in today's class for the new no-volatile memory system is the resistive RAM, LE-RAM. LE-RAM in short. So this type of memory stores data by changing the material resistance, but not the charge, and it has to apply the current and change resistance and the lead as 1 or 0. So they have more advantages, including the low voltage operation, high endurance and small cells which are suitable for dense layer. So here is the picture of the lead lamp. So 5 minutes break, then we're going to resume class after your break time.